In this week's video, we are talking about electronegativity and bonding. We're going to start looking at bond types and at Lewis structures that we draw using Lewis dot diagrams that you've learned about earlier in the year. So the first thing to kind of be aware of is that electronegativity is a number or a value that's specific to each element, and it's something that you can find on your periodic table. So if you don't have that in front of you, pause this for a second and pull out your good periodic table, and we'll look at the back side of that periodic table to find electronegativity. Let me tell you a little bit about what it is first. Electronegativity, which is one big word, but we abbreviate it as EN typically, is defined here as the tendency of an atom in a bond to pull electrons toward itself or away from the other atom that it's bonding with. So as we start looking at electronegativity, it has a lot to do with the things that we've been talking about lately, such as the number of energy levels in an atom and the radius of it, which can affect how much an atom pulls on electrons or how easily electrons can be taken from an atom. It also has a lot to do with the Zeph, or that effective nuclear charge that an atom has. And if you remember, we calculate that by comparing protons and non-valence electrons. So remember what those terms are and look back to some of those things as we talk about this as well, if you don't remember the details of it. Electronegativity doesn't have units, but it is measured on a scale of 0 to 4, with 0 being the weakest attraction or pull on electrons, 4 being the maximum attraction or pull on electrons in a bond. And typically this follows a pattern where you see here the lowest values are in the bottom left corner of the periodic table and the highest are in the upper right. Now, we haven't talked this year about ionization energy yet. So this ionization energy here, we aren't going to be able to kind of refer to this just yet, so don't worry about that. But it follows the basic pattern of lowest in the bottom left and highest in the upper right. So on your periodic table, down in the bottom left corner of your periodic table, you'll find francium. And there it is, with the lowest electronegativity of all the elements at 0.7. The highest is in the other corner of the periodic table, fluorine, at 3.9. So that's a pretty high electronegativity. Basically, it's about 4, which is the maximum. It's important to remember that no atom has no electronegativity, or a 0 electronegativity, because that would mean that the atom has no pull at all on electrons. And because every atom has at least one, if not many, protons, even those atoms that have the lowest amount of attraction still have some attraction. It's not 0, it's just low, because their protons will always pull a little bit on the electrons that are nearby. In general, you'll see at the title here, metals tend to have lower electronegativity values, while nonmetals tend to have higher ones. And here are just a few elements that we've pulled off the periodic table to show you kind of a sampling of that. With the extremes here first, francium and fluorine. Francium with 0.7, fluorine 3.9. And hopefully you're able to find these little green numbers on the back side of your periodic table. It's the only green number there on the right side of all the numbers that are listed. Sodium, another metal, very low, 0.93. Aluminum, a metal, a little bit bigger, but still on the lower side of our 0 to 4 scale. Chlorine, pretty high, 3.16. Oxygen is the second highest of all after fluorine at 3.5. And hydrogen, getting toward the middle again, a little bit more like aluminum at 2.2. So kind of in between, but still on the higher side. Okay. We use electronegativity then to determine and figure out what sort of bond is going to form between two elements. So electronegativity is used to determine bond type. The first kind of bond that you've probably heard of before is an ionic bond. Ionic bonds form between ions, but for our use here, they specifically form when the difference in electronegativity between two atoms is greater than 1.66. And when that happens, we find that electrons are transferred between atoms, given and taken, or we should probably say taken and lost. Okay? Sodium chloride is an example of a compound that forms an ionic bond. So to figure out the bond type, you just look at those values as they're given here on the periodic table, 0.93, 3.16, and you subtract those two numbers. And if the difference between them when you subtract is greater than 1.66, then you'll find that it's an ionic bond. So for example, here, sodium chloride when subtracted gives us a difference of 2.23, which of course is bigger than 166, and therefore sodium and chlorine would form an ionic bond. Same thing over here for aluminum at 1.61 and fluorine at 3.9. When I subtract those, I get a very large difference of 2.29, which is also an ionic bond because it's greater than 1.66. So we simply look up the numbers, we subtract bigger minus smaller, and then look at that value that we get when we subtract and compare it to our cutoff. 1.66 has been determined to be kind of the cutoff point. Now if the difference between those two is greater than 1.66, it's ionic. However, if it's less, we have this other situation. and that's a covalent bond. A covalent bond forms when the electronegativity difference between two elements is small, less than 1.66. And when that happens, electrons are shared by atoms. So not transferred between atoms, but shared by atoms. And sharing is kind of the other end of the options when atoms form bonds, either sharing electrons or a give and take of electrons in the transferring of them. Water is a good example of a compound that'll do that, because if we subtract its electronegativities, we get a difference of 1.2, and that's less than 1.66. So H and O will give us a difference that comes out to be a covalent bond. I'm just realizing this should be a 2.2 and this should be a 1.3, but it would still be less than 1.66. So that would still be a covalent bond. Another one is carbon with hydrogen, a very, very common bond, especially in biochemistry. And the difference between those two elements is very small, a difference of only 0.35. So carbon and hydrogen have basically an equal pull on electrons, and therefore they form a lot of very common and relatively strong and stable bonds. So, covalent when it's less than 1.66, ionic when it's more, but that's an important kind of magic cutoff number to know. To draw Ionic Lewis structures, the steps, we're going to show you that on the worksheet that hopefully you've got a copy of. If you don't, as I switch here over to the worksheet, you'll want to find yourself a copy of it, or just jot down the examples that we go through here into your notes. This is the step sequence, though, that we'll use for most ionic compounds. It's shown here as the process, basically, for doing Ionic Lewis structures. And if you picked up a copy of the handout from LgGrp, given out in class, you should have these instructions at the top of the page. And we'll follow these for all the ionic compounds. So it's kind of all here in one place. And we're going to start by drawing atoms with their Lewis dots. Each atom, each element's abbreviation with its Lewis dots. You'll notice here it says use a unique symbol. So a unique dot symbol. So you'll see that in various compounds we'll use dots, we'll use X's. Your dot might be an electron, or an X might be an electron, or a little open circle could be an electron. You could use triangles. I mean, don't get too crazy, because otherwise it just gets really messy. And usually 3 different symbols is enough. So here's 3 that are easy to work with. And then what we're going to do when we're forming ionic compounds is we're going to move. And there's that word move. This is like transfer. If you remember in the notes, we said electrons are transferred when we're talking about ionic compounds forming. And so the transfer or moving of electrons from the lower electronegative atom to the higher, more electronegative atom. That makes sense because higher electronegativity, remember, means a stronger pull on the electrons that are going to form that bond. And so the stronger pull sort of wins and takes the electrons from the weaker, less attractive atom, which has the lower electronegativity. So we'll look at examples of that. And we do that until we've reached NGC. And you see down here that that means noble gas configuration. The higher electronegative element kind of gets priority. If I'm the boss of the two, it's because I have a stronger electronegativity, and I better have a noble gas configuration when we're done. And that usually means having 8 electrons, because our noble gases have 8 valence electrons. And when we're done, we draw brackets to show the ions as separate particles with their own individual charge. So brackets and charges. And we'll see that at the end of these examples. All right, let's look at sodium bromide, NaBr. And don't worry about the names if I slip the names in a little bit here. You aren't responsible for the names just yet. But for that compound, we have Na with Br. So take a look at your periodic table. I've pulled those elements out. You can take a look at them here. We want to look at those electronegativities, and we should be able to subtract 2.96 minus 0.93 gives us a difference of 2.03. Remember, our magic number is 1.66. So since this is greater than 1.66, therefore this is an ionic bond. So we're going to form this as an ionic compound between sodium and bromine. And we're going to follow the steps given here for ionic compounds. So let's start with each atom and its corresponding dots. So here's sodium. Here's bromine. I have just one of each. And I'm going to give them their valence electron dots. Now, if you're not real comfortable with valence electrons yet, you may just have to trust that the numbers we're going to put up here are correct, and make sure to go back and review that. But hopefully by now you know how to get valence electrons relatively quickly from the periodic table or from electron configurations or something like that. Sodium ends up with 1 valence electron. So I'm going to give it a little circle there for its valence. Bromine gets 7 valence electrons. So I'm going to give it 7 dots. The next step is to move electrons from the lower electronegative, and that's our sodium, remember, that's 0.93 over here, to the higher electronegative, and that's our bromine atom. So we're going to move electrons from sodium to bromine until the bromine, which is the higher one in electronegativity, has reached its noble gas configuration of 8. Well, it's a really simple first example, but basically all it's going to mean is this electron gets moved over to bromine. Bromine has a stronger electronegativity. Bromine will pull it away from the sodium. Bromine has a much higher Zeph of 7+. Sodium has a Zeph of just 1+. So bromine is going to pull that electron over rather easily. Sodium will then lose it. And once that happens, we'll have bromine, and I'll kind of draw the after over here, with its original 7 plus the one it just took. And we'll have sodium with none of its original valence electrons left. So this is kind of our after on the right. And then we want to show, as we got in the instructions here, we want to show brackets. So we show a bracket around each of these because the sodium and the bromide have nothing connecting them. Notice the electron, one of them in this case, moved from atom to atom, and there's nothing connecting these. There's nothing going back and forth between them or bonding them together directly. But what does come about as a result here is bromine has gained an electron. And when you gain an electron, you tend to have a charge. Sodium has lost an electron, and so sodium will also have a charge. If you're not real savvy or remembering well how we figure out what those charges are, pull up your periodic table, take a look at it, and remember it's a matter of protons and electrons. Sodium started out with 11 protons. Bromine started out with 35 protons. And that's still the case now. But in losing one electron, sodium went from having 11 to having only 10. And bromine, gaining an electron, went from having 35 to having 36. So by moving that one electron over, as we did, we've created an imbalance in electrons, and that gives sodium a +1 charge, and that gives bromine a -1 charge. And so we put those charges up here, kind of above the brackets, to show the charges. And the Lewis structure then for sodium bromide would just be this right here. The atoms with their electrons, the brackets, and the charges. So this remains now a sodium and a bromide, or bromine, and they're two separate pieces. Notice there's that space in between, kind of right in through here. There's still a space where they're not connected. They're just attracted to each other because of their differences in charge. So that's the basic idea of an ionic compound and a Lewis structure for it. Let's look at a couple more examples. I'm going to look at, let's look at K3N. Potassium and nitrogen. Potassium and nitrogen have electronegativities that are very different. So as before, if we subtract 0.82, 3.0, we're going to get a difference between these if we subtract of 2.18. That is also greater than 1.66, therefore this is an ionic compound. Remember, that's our magic cutoff number. Anything bigger gets to be ionic. And so we're going to treat these as an ionic compound. We're going to have 3 Ks. So that's potassium, a potassium, and a potassium. And we're going to have 1 nitrogen. We're going to give them their valence electrons. Potassium gets just 1 per potassium. Nitrogen gets 5. Okay. And then we're going to move electrons from the lower electronegativity, which is potassium here at 0.82, to the higher electronegativity. So our electrons are going to follow the route from potassium to nitrogen because this is a stronger pull on electrons in this bond. So potassium's electrons are going to be easily removed because nitrogen is so much more strong in terms of its electronegative pull. So we're going to move, let's bring it with a color. We're going to bring this electron over. We're going to bring this electron over. We're going to bring this electron over. And in doing so, we've accomplished that noble gas configuration for nitrogen. Nitrogen will have, at the end, its original 5. It'll also have the 3 it just took from potassium, 1, 2, 3. And the 3 potassiums will be sitting with none of their original valence electrons. To show the charges, each potassium has lost an electron, and so is now a positive particle. When you lose a negative particle, you become more positive. Potassium becomes positive. Each potassium has lost 1 electron, so each potassium would have a 1+ charge. And the nitrogen has taken or gained 3 electrons, so that nitrogen now has a -3 charge. If we look at the particles again, do the little count, each potassium has 19 protons. After losing 1 electron, it has only 18 electrons left. and that gives us a charge of 1 plus, which is where that charge comes from. The nitrogen started out with 7 protons and had 7 electrons. It gained 3 electrons, so now it would have 10, and that gives us an overall charge of -3. So you don't have to show, right? You don't have to show this math, but you should be able to, if you're asked to, justify why is nitrogen -3? Because the protons and the electrons aren't in balance. In fact, there are 3 more electrons because it gained 3 than there are protons, and so that's where that charge comes from. It's important that we can explain it if we're asked to. You don't have to on every question, but it's important that you could. I want to show you one more down here, number 6, Al2O3. Now, aluminum and oxygen again, 1.61, oops, what the heck, 3.5. Right? If I subtract those, right, it's a difference of 1.89. Still greater than 1.66, therefore ionic. This whole page is ionic, so you don't have to worry about us trying to trick you. But it's good that you know how to figure that out, because eventually you're going to get a list of compounds where you won't have the type of bond listed already. But I'm going to have aluminum with 2 aluminums, Al2, and 3 oxygens, OOO. Let's give everybody their valence electrons. Well, oxygen gets 6 apiece. Aluminum gets just 3 apiece. I'm going to go with X's for aluminums. Okay. And now we need to move electrons toward the more electronegative element. So hopefully we recognize that that means it's going to go this way, right, from aluminum to oxygen. Much more strength, much more pull. The oxygen is going to sort of take then the electrons from aluminum. And when that happens, then we'll bring these 3 over. 1 will go to oxygen here, 1 will go to oxygen here. And that's all this oxygen can take, because now that oxygen will have 8. Its original 6 plus the 2 it just took, that's 8. So that oxygen's sort of reached capacity, or reached a noble gas configuration. So this one that's left, we could say will go to this oxygen, and this one will go to that oxygen as well. And now that oxygen is complete. It's going to have the original 6. It's going to have the 2 it just took. And that's 8. That's a noble gas configuration. And then aluminum's remaining ones can go to this last oxygen. So the way this kind of works out, for everybody to kind of work out a perfect sort of situation, it takes 2 aluminums giving electrons to 3 different oxygens for the ratio to kind of work out. 2, 3, there it is. Okay. So this is what we're kind of left with. Now each of these oxygens has taken 2 electrons and would then have a -2 charge. Each of the 2 aluminums has lost 3 electrons and so would have a 3 plus charge. And we want to look finally at then that noble gas look one more time in terms of the count of electrons and protons. This aluminum now has 13 protons and only 10 electrons because it lost 3. So not only does that explain why it has a 3 positive charge, it lost 3 electrons, and so now it has 3 more protons than electrons. But we would also be able to look at that and say, because it has 10 electrons, this aluminum is neon-like. In other words, it has the same number of electrons as a neon atom, and that's a noble gas. And that's what the elements tend to do. They bond in a way that gives them a configuration like a noble gas. The same thing can be said of oxygen here, because these oxygens, each of them, would now have 8 protons. They've each gained 2 electrons. That makes 10 total for a charge of -2. And that explains the charge, but again, that atom is also neon-like. And if we go back and look at most of the examples that you'll come across in this page, it's always the case that the more electronegative element, in this case the oxygen, ends up like a noble gas. But it's also often, but not always, the case that the less electronegative element, in this case our aluminum, ended up as a noble gas as well. Doesn't have to work out that way, but it did here. So those are our Lewis structure examples. Work through on this assignment. If you're coming out of the large group work, we want you working down as far as number 11. Once you go past 11, there is a little bit of a complication on the next 5. So we'll work on those with you in small group class. And then the covalent ones on page 2 will be hitting in small group class as well, or in a separate video to be posted at a later time. So hopefully that helps you get a good feel for ionic compounds. Follow those steps and these examples to kind of help you out. And remember to always look at those electronegativities and make sure you understand why this is an ionic bond. Make that quick subtraction If you know it's greater than that 1.66, you know what kind of bond you have, and you should proceed with brackets and charges outside of the brackets. If you have questions, talk to one of your teachers in small group, and thanks for listening. We'll talk to you later.